Hey everyone. In this video, we're going to be talking about Chapter 8, Lecture 19, Learning Objective number 9. So we're going to be looking at our bond enthalpies. We'll be using bond enthalpies in order to calculate reaction enthalpies. So when we talk about the idea of a covalent bond strength, we're basically saying how much energy is required to break that bond, or how much energy is released when that bond is formed. So if it's energy to break the bond, that's going to be a positive value. So this would be a positive kilojoules per mole. And then when the bond is formed, this is going to be a negative kilojoule per mole. Okay, so we call this bond enthalpy, this kilojoule per mole value. And anytime you break a bond, it will always require energy. Anytime you make a bond, it will always release the energy. And we're talking about individual bonds. For instance, if we talk about Cl2 molecule, in this molecule, when we're looking at the Lewis structure, we see that we have a Cl-Cl single bond, and that has a bond enthalpy equal to 242 kilojoules per mole. So 242 kilojoules a mole are required to produce 2 Cl molecules, like so. Cl atoms, like so. Same thing can be said if we reverse the process. So if we take our chlorines, we add them back together, we're going to release that energy. Very similar to what we saw with lattice energy, but much smaller values. Our average bond enthalpies will be given in a table. So these are going to be tabulated values. And they're going to be an average over a bunch of different molecules with those types of bonds. So it won't necessarily always be that same exact energy, but we can use it as a starting point or use it as a means of calculating rough reaction energies. Now, our bond enthalpies will always be positive. The values that are given in a table will always be positive. Because it's always talking about how much energy is required to break that bond. But if we are forming that bond, we'll just put the negative sign to indicate that. The value of that bond enthalpy is going to be based on what atoms are involved in that bond and what type of bond it is. So by type of bond, I'm talking about whether it is single double, or triple. When we go from a single bond to a double bond, we increase our number of electrons that are being shared, and we decrease the distance between the atoms, so it's actually harder to remove or break that bond. So we're thinking about bond strength. A triple bond will be the strongest, followed by a double, followed by a single. That's because there's more electrons that are being shared. And then if we think about bond length, it's going to go the opposite way. Our longest bond length is a single, followed by a double, followed by triple. So not only is the bond strength dependent upon the fact that it is, or the triple bond being stronger because it's sharing 3 pairs of electrons, but it's also a shorter bond. So thinking about it in terms of electrostatic potential energies, it's got more electrostatic potential energy because you're putting the charges closer together. Okay. So when we try and solve for our reaction enthalpy, we're going to use our bond enthalpies. Okay. So you're going to use a table of average bond enthalpies, and you're going to basically take the bond enthalpies for the bonds that are broken and subtract out the bond enthalpies for the bonds that are formed. So your delta H of your reaction will be equal to the sum of the bond enthalpies for all bonds broken minus the sum of bond enthalpies for all bonds formed. Okay. So, for your bond enthalpies, as I said earlier, you'll just, in here, these bond enthalpies, you're just going to use the tabulated data. Use tabulated values. So they will all be positive. And we just take into account the exothermic nature of the formed bonds with that negative right here. Okay. Now, when we have a reaction, if the bond's broken, or the energy to break bonds is greater than the energy of the bonds formed, we are going to have an endothermic process. So we'll have a delta H of reaction that is positive. If the energy of the bonds broken is less than the energy of the bonds formed, then we're going to have an exothermic process, and our delta H of reaction will be negative kilojoules per mole. Okay, so let's try an example. So I'm going to go through the steps and then we'll try an example. So our steps, fairly easy. First, you're going to balance your equation. We need to know how many of each bond we have. So in order to do that, we have to have a balanced equation. Then you're going to draw Lewis structures. for all molecules in the chemical equation. We need to know how many of these bonds we have, but we also need to know what types of bonds we have. Very important. And then 3, put values into the equation above. I will include a average bond enthalpy table on D2L along with your test. So these are not things you need to memorize. Okay, so if we take the following reaction, N2H2 goes to N2 plus H2. We want to find out what our enthalpy of reaction is. We need to take our bonds formed minus our bonds broken minus our bonds formed. So we need to know what type of bonds we have, and we need to know how many of each. If we look, this is already balanced. There's two nitrogens, 2 hydrogens on both sides. Good to go. Next, we want to draw out our Lewis structures. And when we do, that's our N2H2. Then it goes to N2 and H2. So we see on our bonds broken side, or our product or reactant bonds, we have 2 NH single bonds and 1 NN double bond. Bonds formed. We have 1 nitrogen-nitrogen triple bond, 1 hydrogen-hydrogen single bond. So we then go into a bond enthalpy table. There's one on your PowerPoint if you want to watch and play along. But what we'll find is that if we look at an NH bond, it has an energy of 391 kilojoules per mole. And a nitrogen-nitrogen double bond is going to have an energy of 418 kilojoules per mole. Then we look for a nitrogen-nitrogen triple bond at 941 kilojoules per mole. You can see going from the double bond nitrogen-nitrogen at 418 to triple bond 941, a significant change. A nitrogen-nitrogen single bond is 163 kilojoules per mole. So it exponentially increases as we change that bond from a single to a double to a triple. And then our hydrogen-hydrogen single bond is going to have an energy of 436 kilojoules per mole. So to solve for our delta H of a reaction, we're going to take all of our bonds that are broken, add them together, and then subtract out all the bonds that are formed. And when we do this, we get a value of, 1 second, negative 177 kilojoules per mole. So this is going to be an exothermic process. And that is it for chapter 8. See you guys later.